Okay, so now that we've just seen an example of a couple examples of sequences, a closed formula and a recursive formula. So in those examples, we were given the formula and we wanted to calculate the values of the individual terms of the sequence. So suppose we want to go in the other direction, right? So we have some numerical sequence. So here are the first 5 terms of the sequence, and then they continue in this pattern. And we want to figure out how to write down a closed formula or a recursive formula for it. So the idea is that, say we have a sequence of numbers that follow some kind of pattern. We want to try to figure out the general pattern so that we can calculate all of the terms in the sequence if we wanted to. Right, so to figure out the formula, so you want to try to look at the numbers in the sequence and try to figure out a pattern to it. So a good idea to start is to look at consecutive terms and see if there's a common relationship between them. And so if we look at the successive terms here, we'll notice that to go from -1 to 3, we add 4. Then to go 3 to 7, we add 4. To go from 7 to 11, we add 4. Then to go from 11 to 15, we again add 4. And so the whole sequence is following this pattern of adding 4 each time. Right, so this is a sub 1, a sub 2 is 3, a sub 3 is 7, a sub 4 is 11, a sub 5 is 15, and so on. And so we can guess the next few terms in the sequence by just following this pattern, right? So if I wanted to write down a sub 6 will be a sub 5 plus 4, which is equal to 19. And then a sub 7, again, I take this and I add 4, would be 23. And so on. Okay, so we're going to use this idea. So let's first write a recursive formula for it, because that's essentially what we're doing here, right? So I described the next term a sub 6 in terms of the previous term a sub 5. So let's do the recursive formula first. So to describe the recursive formula, I need to know first the value of the first term in the sequence. So a sub 1 is equal to -1. And we see that we're adding 4 each time to the previous term, right? So a sub 2 is equal to -1 plus 4, right? And then a sub 3 is equal to a sub 2 plus 4, right? So add 4 to the previous term, and then a sub 4 is equal to a sub 3 plus 4. So this is the recursive pattern. And so the way I write it is that a sub n is taking the previous term in the sequence, which is a sub n minus 1, and then adding 4 to it. So this is the recursive formula. Okay, so now let's try to get a closed formula for this. Okay, so let's try to write out the recursive formula, right? So a sub 2 is -1 plus 4. So let's use this recursion and plug it in to see what we get. So a sub 3 is equal to a sub 2 plus 4. That's the same as -1 plus 4 plus 4. And then if I plug a sub 3 into a sub 4, I get a sub 4 is equal to -1 plus 4 plus 4 plus 4. So I can say that a sub 3 is -1 plus 2 times 4, and then a sub 4 is equal to -1 plus 3 times 4. And so each term in this sequence is some -1 plus some multiple of 4. So I need to figure out how this number relates to the index, right? So this number 2 is just one less than the index. This number 3 is one less than the index. This 2, same as 3 minus 1, and then this 3 is the same as 4 minus 1. So you just take the index and subtract 1. Right, so that's how we'll get the closed formula. So the closed formula a sub n is equal to, so you start with -1, and then it's 4 times, and then this number is just the index minus 1. Here the index is n, so index minus 1 will be n minus 1. Or if I want to simplify this, I can write this as 4n, -1 minus 4 is minus 5. You can check that this is correct. This should be 4 times n. You can check that this is correct, right? Because when n equals 1, you have 4 minus 5, which is -1. When n equals 2, 8 minus 5 is 3. When n equals 3, 12 minus 5 is 7. So we get back the terms of the sequence using this formula. So this is closed formula, and then this is the recursive formula. So this example is an example of what's called an arithmetic sequence. So any sequence where the successive terms are obtained by adding the same number over and over again, this type of sequence is called an arithmetic sequence. So let's take a look at an example of a different kind of sequence. Suppose my sequence now is the following sequence: 1/3, 2/3, 4/3, 8/3, 16/3, and so on. And so same as before, I want to figure out a closed formula and a recursive formula for this sequence. Right, so I again look at successive terms. Looking at successive terms in the sequence, the pattern is slightly different this time. Right, so here the denominator stays the same, but you can see that the numerator is doubling each time. So to go from 1/3 to 2/3, multiply by 2. To go from 2/3 to 4/3, we again multiply by 2. Then 4/3 to 8/3, multiply by 2. And then 8/3 to 16/3, multiply by 2. And then so the pattern is going to continue. So we see that a 6 would be twice as much. So 32 over 3. A sub 7 will be twice as much again, so 64 over 3, and so on. Okay, so we can easily get the recursive formula again. So a sub 1 is equal to 1/3, and then each term, which we've just described, is twice the previous term. So it's 2 times a sub n minus 1. So that's the recursive formula. So now let's get the closed formula. Okay, so let's write out a few terms, and we'll see what the closed formula should be. So a sub 2 is 2 times 1/3. A sub 3 is 2 times a sub 2. But a sub 2 is 2 times 1/3, so this is 2 times 2 times 1/3. So this is equal to 2 squared times 1/3. A sub 4 is 2 times a sub 3. So 2 times 2 times 2 times 1/3, or 2 cubed times 1/3, so 1/3 times 2 cubed. And so here the thing that's changing from each term is now the power of 2, and you can see that the power of 2 is always 1 less than the index. So this gives us a closed formula as 1/3 times 2 to the n minus 1. Okay, so this kind of sequence where to go from each term to the next, you multiply by the same number each time. So this is what's called a geometric sequence.